So, continuing with the types of beams, as I said earlier, depending upon the types of support on which the beams are laid, so the beams can be different types: simple, continuous, or cantilever, as we have studied in the previous slide. So, other types of beams are fixed, prop cantilever, and overhang. As you can see in the fixed beam, both of the ends of the beam are fixed supports. That means it won't be able to have any rotational or any static movement over there. That will be maintained under static equilibrium completely. And as you can see in the prop cantilever, one side is fixed and the other end is roller support. And an overhang beam, a beam is extending towards more than the support. It is extending over the support. Like you can see, there are one hinge support, one roller support in between, and the one end is totally free. So these type of beam is called overhang beam. Moving ahead, so analysis part, as we can see, we need to develop a free body diagram. So what is this free body diagram? See, as I've told earlier, applied load will be resisted by the reactions by the supports. So free body diagram is nothing but the outlay of what are the forces are being subjected to the beam and the reaction force generated. So let's just take an example. This is a simply supported beam. As we can clearly see, one end is hinged and one end is roller, and a blue arrow indicates a downward applied point load. So due to the applied load, some reaction will be generated. The reactions are being depicted by the green arrows. So hinged will be developing two reactions as by its own property, and the roller will be generating only one reaction upward. As you can notice, there is a one solid arrow, green solid arrow, and one dotted arrow. The dotted arrow is indicating that there won't be any reaction, because as there is no horizontal applied on the beam, there won't be any reaction to it. So there will be only two reactions at both ends, that too in vertically upward direction, as the applied load is in downward direction. So this is nothing but a free body diagram which is showing how the applied loads and the resisting forces and movements will be developed. So the fundamental principles of equilibrium, which states that if the beam is to be in static equilibrium, these three conditions must be satisfied. The summation of forces on all the x and y directions should be equivalent to 0, and the summation of moment throughout the beam should be equal to 0, so that it remains under equilibrium. So this is the basic of our analysis, that any point, any cross section in the beam must be under equilibrium. So let me first of all define what is a moment. A moment is nothing but which is generated by a force only. In this figure, I have shown a cantilever beam. As you can see, one side is fixed and one side is free. So what if I apply a point load at the free end? Suppose an F load is applied at the free end. As you can see, will be a moment generated M at the fixed end, which is equal to the force into the perpendicular distance. So moment is nothing but, if this is a beam supported at one end, and if we apply a point load, a moment will be generated which will try to rotate the beam about this point. So moment is nothing which try to rotate the beam. So force into, we can generally calculate it by force into the perpendicular distance. Higher the force and the way away the distance the force is applied, the more will be the moment generated. So here I have plotted a beam. Suppose a beam is simply supported, one end is hinged and one end is a roller, and 3 point loads are subjected at 5 kilonewton, 10 kilonewton, 8 kilonewton at a distance of 4 meter from the left side support, 1 meter from the right hand support, and one in between at point D, as you can see, 10 kilonewton. So if, for example, the reaction due to this force is 8.2 kilonewton on the A point and 14.8 kilonewtons on B point, these reactions can be easily calculated by the help of the previously discussed static equilibrium equations. But suppose in our civil engineering, we need to design the beams for shear forces and bending moments. So what is this shear force and bending moment? Suppose within the beam cross section, I need to find out the shear force. So I want to know a shear force at a distance 6 meter from the left hand support A. So how will I find it? In order to do this, we first need to make a cross section XX at a 6 meter from the left hand support A, as shown in the figure. This pink line is denoting a cross section XX that I wish to know what will be the impact on this cross section due to the applied forces and the reaction, which is at 6 meter from the left end. Imagine the beam is cut into two half pieces at cross section XX and it is separated. So the next figure will be showing the two separate pieces of the beam separated at 6 meter from the A end or 9 meter from the B end. So in order to determine the impact of the forces and the reaction, let me apply static equilibrium equations. So to find the forces experienced by the section, consider any one part of the beam as taking on the left hand portion. See, upward forces I am considering as positive and the downward forces I am considering as negative. So the net transverse force experienced will be in the left part will be 8.2 plus and the minus 5. So the net motion will be, or the net force will be 3.2 kilonewton upward, as upward because 8.2 dominates over the 5 kilonewton. Similarly, we can calculate also moment. Moment is, as I stated earlier, moment is nothing but force into perpendicular distance. So the point where the cross section is cut, I want to know the moment over there. As from the left hand side, you can see there are two forces, 8.2 kilonewton and 5 kilonewton. Both will generate moment as per their magnitude. So calculating moment, first moment will be 8.2 kilonewton into the 6 meter, and this direction will be clockwise, and other moment will be 5 kilonewton into 2 meters. 6 minus 4, as you can see the total distance 6, and the distance of distance between the 5 kilonewton and the point of cross section is nothing but 2 meters. 6 minus 4, so 5 into 2, you will get the answer 39.2 kilonewton meter, and the net direction will be clockwise. Although the 5 into 2 kilonewton is anti-clockwise, that's why it is taken as a negative, but the 8.2 kilonewton force dominates over the anti-clockwise moment, so the net rotation, your net moment direction will be clockwise. Similarly, if we analyze the right hand portion, if we consider the right hand portion, the transverse force through the same convention, upward means positive 14.8, downward minus 8, downward minus 10, the net is 3.2 kilonewton, which will be in the upward direction, which will be in the downward direction, as it is dominating over the 14.8 kilonewton. And similarly, calculating the moments, we will be getting the answer 39.2 kilonewton meter. So it is a very special thing to notice over there. From left side, I got the answer 3.2 kilonewton upward, and clockwise 39.2 kilonewton meter moment. And from the left hand side, I get the same equal magnitude but in opposite direction, a shear force of 3.2 kilonewton and a moment of 39.2 kilonewton meter in anti-clockwise direction. And if I join both the diagrams, the net summation will be 0. So this is what nothing but the shear force and bending moment is. If at any particular cross section the summation of the left hand forces is termed as shear forces,